A wheel is a circle. But what makes a circle so special when it comes to rolling? A circle is a shape of constant width. This means that the distance across the circle, measured through its center, is always the same. No matter how you rotate a circle between two parallel lines, the distance between the lines stays the same. This property is crucial for smooth rolling. This constant width is what allows wheels to roll smoothly. It ensures that the wheel maintains a consistent height as it moves. If a shape did not have constant width, it would wobble as it rolled. Imagine the chaos of a ride on a misshapen wheel. Imagine a square wheel trying to roll. It would bump along because its height changes as it rotates, making for a very uncomfortable journey. The height variation causes the wheel to bump along the path, disrupting the smooth motion we expect from a wheel. The same principle applies in 3 dimensions. A sphere, like a ball, has constant width in every direction. A sphere, like a ball, has constant width in every direction. This is why balls roll so smoothly on various surfaces. This is why ball bearings work so well. They reduce friction and allow for smooth, consistent motion in machinery. But what about higher dimensions? Can the concept of constant width be applied beyond our 3-dimensional world? Can we have wheels in 4, 5, or even 1,000 dimensions? Turns out we can. The principles of geometry extend far beyond what we can see. In the 1980s, mathematician Oded Schramm asked a fascinating question. Could we make shapes of constant width that were smaller than a sphere? In other words, could we find shapes that would fit between those parallel lines, but take up less space? This was a tricky question because it challenged our intuition about shapes. We're used to thinking of circles and spheres as the most compact shapes of constant width. Schramm's question puzzled mathematicians for decades. It turns out the answer is yes, and the solution lies in higher dimensions. A new generation of mathematicians has finally cracked the code. They have been working tirelessly, combining their knowledge and creativity to solve one of the most intriguing problems in geometry. They found a way to create smaller, constant-width shapes using a surprisingly simple method, intersecting spheres, or more precisely, n-dimensional balls. This breakthrough has opened up new possibilities in the field of geometric shapes. Imagine 2 soap bubbles floating towards each other. As they drift closer, they begin to touch and interact in fascinating ways. When they touch, they form a flat surface where they meet. This simple interaction is the key to understanding how these new shapes are formed. Now imagine this happening in higher dimensions, with hyperspheres instead of soap bubbles. The concept becomes even more intriguing and complex. By carefully choosing the positions and sizes of these hyperspheres, mathematicians can create a wide variety of new shapes. Each configuration leads to a unique and fascinating result. These shapes are like many-sided guitar picks, with smooth curves instead of sharp edges. They represent a new frontier in the study of geometry, blending simplicity with complexity in a beautiful way. Section 4. Rolling into the future. These new shapes, called Schramm orthogonals, are remarkable for several reasons. First, they are smaller than hyperspheres of the same width, answering Schramm's question. Second, they can be created in any number of dimensions. This means we can now visualize and study wheels in spaces we can't even imagine. Finally, the method used to create these shapes, intersecting hyperspheres, is surprisingly simple and elegant. It's a testament to the power of geometry to solve complex problems. Section 5. New dimensions of understanding. The discovery of Schramm orthogonals opens up exciting new avenues in geometry. These unique shapes, which defy traditional Euclidean principles, offer a fresh perspective on how we understand space and form. For one, it challenges our assumptions about what shapes can exist. The implications of these findings stretch far beyond theoretical mathematics. It also provides new tools for studying higher dimensional spaces, which have applications in fields like physics and computer science. Imagine being able to visualize and manipulate dimensions that were previously thought to be purely abstract. This breakthrough is a reminder that even in a field as ancient as geometry, there are still mysteries to uncover and new worlds to explore. The potential for new discoveries is immense, and the journey has only just begun. Who knows what other strange and wonderful shapes are waiting to be discovered in the vast expanse of higher dimensions? The universe is full of secrets, And with each new discovery, we come one step closer to understanding the intricate tapestry of reality.